let's keep this moving. I hope you all enjoyed it. I hope you've been having a good time. Youlong, are you around, man? Are you here? Can I call you to the
Yes, I'm here.
stage? There he is. Okay, so I just want to give you a heads up because we had a little bit of audio difficulty on the last chat. So in case that happens again, we may have to restart this. Nothing major. Everybody sit tight. But just in case it happens again, we'll restart it. Now, it should be good. If you don't see me, then we're all good. All right? So if you cannot see me, we're fine. And I'm going to just hand it over to you, man, because you're coming at us all the way from ByteDance. This is super cool. I am very addicted to some ByteDance products. And I will just say, I want to know how you recommend things because I love it. All right. We're going to have questions for you afterwards. So everybody in the chat, please be asking your questions. And I'm going to hand it over to you, man. Youlong, it's all yours. The floor is yours.
Hey, should I present or someone else gonna help me?
It's already presenting, my man. You're good.
Okay.
Yeah, you should see it on the screen.
Okay, cool. Yeah.
All right. See you later, dude.
Okay, great. So yeah. Hi everyone. My name is Youlong Cheng. I'm an engineering leader at applied machine learning team at ByteDance. My team is mainly focused on machine learning infrastructure for recommendation modeling and also some foundation algorithm. Today, I'm going to talk about a new machine learning system called Monolith. So this has been published as a paper in recsys 2022 this year. The full name of this paper is Monolith, Real-Time Recommendation System with Collisionless Embedding Table. Okay, so sounds like I should share my screen. Oh, no. Okay, so I will break down this talk into three sessions. One is overview, the second one is technical detail, and the third one is open source. Okay, yeah. First of all, let me talk about some background. So what's the scenario? What's the problem we try to deal with? I think it's just a very large scale item recommendation. So here the item could be the short video recommendation or the ads recommendation. And in this scenario, we prefer some instantly feedback from user because if you can capture the user's short interest faster and change your recommendation result quickly, this can help improve the user's experience. And from the model architecture perspective, it's very traditional, typical, and wide and deeper family. So here in the wide and deeper, you should have something called the sparse embedding. So the sparse embedding is meaning for storing the categorical features like the user ID, item ID. And the deep part, you have a lot of dense operation. Those dense operations is mainly for the high order interactions. So here you can see a very typical model architecture. So in the bottom, you have a bunch of IDs. Those are the inputs to your training system. And you have a layer called embedding layer. So we needed to look up those embedding from the embedding storage to get each person or each video ID's representation. And the middle left side, you can have the typical FM layer. So FM layer is mainly focused on the explicitly modeling some interaction between the user side feature and item side feature. And the MLP is also mainly for capture more high order interaction, which is not easy to directly explain. And then at the end, we are going to sum them together to predict the final score as output. So this is the very typical model architecture we use and we try to run for this recommendation system. Yeah, next one. So we are going to talk about some limitation of existing solution. So I think there are two different limitations. First of all, undesirable collision of ID in embedding tables. As you can see, the TensorFlow or PyTorch, they use the variable to represent the embedding table. So here, when you define some user embedding storage, you need to call the variable. You need to provide the vocab size and the embedding dim. So essentially, this is a matrix. The vocab size is needed predefined. And when you do the lookup, your ID's embeddings to this embedding table, the common approach is you might use your ID, like UID, you module by the vocab size, and then map to the corresponding row and get the user embedding. But if your ID pool is very large and your vocab size is not big enough, high likely you might see some collision, like you might map two different user ID into one row or even more. So this is something is undesirable. And the second thing is, giving this dense variable as embedding table, it's hard to do the real-time update for online models, because every time if you need to update some embedding, you need to update the entire embedding table. It's very costly from the computation or from the network bandwidth perspective. So those are two things we feel is not really be solved in existing machine learning system, and this is something we want to improve. Next one, please. Yeah, so first of all, we want to show some high-level result. So you can see here, we found if we switch from the dense variable to the collision-free hash table, we can see clear win in the model training. So the left figure is some training experiment we did in some public data set like moving lens. You can see the blue line is some collision-free hash table approach, and the orange line just the traditional dense variable solution, which has some hash collision. You can see we have clearly AUC win. And the right side is also another production model we tried. You can also find out the collisionless hash table can have a clear win comparing with the older approach. Next. Yeah. And the second thing I want to emphasize is real-time updating is super important. So more frequent model updating can result in better online model quality. So the right figure is some, we did one experiment. We're comparing with 3 different setups. One is like we only sync the training and the serving model every 30 minutes. And the other one just we sync them every 1 hour. And the third one is we sync them every 5 hours. You can see there are clear win. If you sync them more frequently, your online serving model performance can be better than you sync them infrequently. But there's some trade-off between how frequent you want to sync between your training and the serving. Yeah, next, please. Yeah, I'm going to talk more about the technical details. So, as we just mentioned, the fundamental thing is we want to use something called collisionless embedding table. So here is one example, like in our system, how to represent a collisionless embedding table. We call this as a feature slot. So you in this feature slot, there's a name. You must give them a name, and there's two different feature. One is bias, one is vector. Bias is meaning single float. The vector means just the more floats, just a real vector. So a user, when you define this embedding table, you need to provide a few things. First of all, you need to tell the system how to initialize this embedding, and also you need to configure what's the optimizer you want to use. For bias, I think the most popular one is FTIL. For vector, AdGrad should be the most popular optimizer. And you also need to do some learning rate scheduler, because in some machine learning training system, you need some warm-up. Then during warm-up, the learning rate is gradually increased. And also we need to provide a few things called like expire time. So this is a trade-off. Like suppose you don't want any collision, but your system do receive new ID every day, then if you don't do any expiration, your model can be explode. Then we define something called expire time. So this means some ID feature, if you in this system for a few days, has not be touched from the system. So we're gonna try to evict this ID from the embedding table. This can guarantee the model size maintain a reasonable constant over the time, and we will not see any explosion. Yeah, next one, please. And we want to do some real-time training. So how to do real-time training? Your training data must come from some queue. So in our system, we directly implement some Kafka data I/O. We read from Kafka. And one problem for online training is the reliability is not easy to maintain, because for online training, your system must run for a few weeks or for months without any intervention. Then how to achieve the good reliability is some challenging problem. In our system, we just using some daily checkpointing, just every day in the long peak time, we try to dump the training private server to some storage, data storage. And then if your single shard private server machine or the container is down, so we are going to recover from the recent checkpoint. So this in this case, so we don't need to worry about we lose all the training data. We still can get a few some relevant recent checkpoint from our storage. And also based on our statistic, like in some typical data center, one out of 2,000 machine might die every day. Then suppose you are doing online training for a giant model, then you do see a few failures over the time. Then with this auto recovery approach, we can guarantee your model can be trained, can be served for months without any human intervention. Yeah, and the also we need to guarantee the system can support real-time updating. So here, real-time updating, we just update two things. One is the sparse embedding, one is the dense. For sparse embedding, just which is mentioned, we cannot afford to update the entire embedding table in real time, because suppose you are 20 terabyte model, then it's infeasible to update. You need to cost a lot of network bandwidth to update them. But think about in real time, how many items really be update in the past few seconds? Maybe only a small portion of them. Then if we use this incremental approach, we only update those ID embedding which has been touched in the past 1 second. Then the volume, the communication volume can be decreased a lot. And for the dense parameter part, we just use the traditional approach. We update them in every few minutes. So in our experiment, we found this is good enough for maintain good A/B experiment result. And for a typical recommendation model, so we use in like 100 megabyte per second sparse embedding update for one replica. Yeah. Now let's talk about some engineering metrics. So the model size, we can support we have tried up to 20 terabyte model, and the serving QPS we have been using like 20K with 5 replica. Each replica contains 30 container or shards, and our system can support very flexible deployment. If your model is not too big, if a single machine RAM can host the giant embedding, then we can support a single host. If the model is bigger, then we can also support multiple hosts to sharding the giant embedding table. Yeah, and here we want to highlight some features. So Monolith is ready for use in production. It supports batch training, stream training, real-time weight updating, and it embraces the TensorFlow ecosystem. Like we use the standard TensorFlow serving as a serving system, and it's flexible for both CPU training, GPU training, and serving. And it's going to open source as a standalone library with Apache 2.0. So you are free to use Monolith at your own institution. So, and also Monolith is part of our BytePlus recommendation products, and we have been seeing a few successful cases which use Monolith and get their business win, like for some e-commerce customer, and for some short video, and also for some other ads modeling. So using Monolith can boost their call matches 20 or 30 or even 40%. Yeah, next please. Yeah. And the system is compatible with the open source ecosystem. We're fully compatible with TensorFlow. We are just build a middle level system based on TensorFlow low level runtime. So we are able to plug in TensorFlow extended features like data service. And migrating from the old TensorFlow or PyTorch model to Monolith just is not so hard. So minimal change can be done, and then we can migrate. And we use some standalone TensorFlow serving solution. We use standalone TensorFlow saved model. So that means the model you train in the Monolith, you also can serve that in on-prem or even in cloud or in your own data center. So you are free to bring the model you train to everywhere and deploy them everywhere. Next one. Yeah, that's all my talk. Yeah, thank you. Any questions?
Well, thank you very much. So we've got a few questions that have come through, and if you have a minute, I want to ask you them. Is that cool?
Sure. Yeah.
All right. So let's go with one from Anne. You're happy dealing with latency, cybersecurity, and compute demands variations on-prem. That's good. Great. So did you ever attack? All right. Would you? Sorry, you caught me a little off guard with this. So here we go. Would you recommend this system for companies' applications that are a lot smaller than ByteDance?
Yeah, I think it's up to whether your data is enough, right? If your current data has a lot of user interaction, then then I think no matter how big your model is, this can definitely give some gain, because first of all, even you don't use any real-time training, you can use this hash table implementation. This can guarantee low collision. Then low collision itself can already bring you some gain. And if your company, if your system need to deal with a large volume of the user action, then try to also use this real-time updating. So this also could give you some boost for your model quality. Yeah, I think overall, I feel no matter how big or how small your scenario, just to try it out, usually you will see some gain. But the how much gain is all depend on your baseline, what your baseline is.
We'll wait a second to hear what the baseline is. So while we're waiting on that one, can you talk a bit about some example sparse features you use?
Oh, I think the most important sparse feature just from the item side, like the item ID. Like suppose you are a e-commerce business, right? The SKU ID can be converted to as the item ID, the good ID, and also the features you can use. I think for a user side, just the user ID is one important feature, and also the user behavior, like what's the recent interaction, like the recent goods they bought or the clicked. This can be a sequence feature. It's super important. And yeah, I think for feature engineering, yeah, you can also just try to build more and more ID features, and using this system, they can learn their embedding in the long run, and they can boost your model quality.
Okay. How'd you choose the name Monolith? Seems to be an anti-pattern with negative connotations these days.
Yeah, I think we just want to build a end-to-end solution, and we believe in the older approach for recommendation. Just that people use different parts. You use different open source solution is not ideal. So we want to build a closed loop solution and support both training, serving, and even in the long run, we want to support more feature engineering. We believe a monolithic repository and support all the needs for recommendation is the user really need.
Makes sense. All right, so we've got so many great questions coming through here. Thank you all for asking them. I'm going to ask one more, and then we're going to jump to some trivia because I got to give out more swag. I got a quota of swag that I got to give out, and so that's going to happen. Now, last one for you. I would like to know. Oh man, it's so much pressure's on. Which one is going to be the last one? How can you be sure that your models are safe against adversarial attacks in the case of online learning? And did you ever identify such attacks?
To be honest, we haven't been thinking about any attack, right? Because your model is your own. You serve your model only your. Oh, so you worry about some user might create some fake events and cause some problem for your model. I think that's something your security team should prevent this happen. Yeah, usually in a system, we assume all the user behavior are real, are correct. Then we just train. Yeah, we don't want to worry too much about those attacks. I think that's some security team should take care.
Perfect, dude. Awesome stuff. Thank you so much for putting out the paper. I think it's incredible the transparency that you were able to give and the help you get to show us what you are doing. So thanks for coming on here. I thoroughly enjoyed it. And for everyone that has more questions for you, I'm going to direct them to the chat, and maybe you can jump in the chat and answer some of those questions, because there's a ton coming through. People were stoked on this.